So my name is Michel, and I'm delighted to welcome today Dr. Lew Lim, who has agreed to talk to us about photobiomodulation as a promising treatment for Parkinson's. Before we listen to Dr. Lew Lim, I'd like to say a few things. First of all, as you have all heard, the session is recorded. The benefit of this is that we're going to post it on a YouTube channel, which is relatively recent. It is called No Silver Bullet for PD in one word. So No Silver Bullet number 4 PD in one word. And you can see there other videos of previous discussions, as well as the one, of course, that will be posted tonight. I'd like to remind everyone also that the information provided during the session is for educational purposes only. So it is no substitute to medical advice. We all know it, but I still would like to say it. So participants are advised to consult with medical professionals if you're seeking medical advice, diagnosis, or treatment. We will be quite a few people on the line today, so we will take the questions at the end of the talk. In the meantime, what I would just suggest that you do is that you, when questions come through your mind as we progress through the presentation, is that you put them on the chat. So just a few words finally about our group. As some of you know, because you were there from the start, but not everyone does, basically our group came together in the summer last year when some of us took part to a nutritional seminar on Parkinson's and decided to stay in touch after that. It was 3.5 days, and we created a WhatsApp chat that became over time a Slack channel. And we decided to call ourselves No Silver Bullet. It is a very informal group of people with Parkinson's. The name reflects our holistic belief, that our belief in a holistic approach to basically managing our symptoms. No silver bullet will take care of us, but a combination of various elements will help us get better. We started having external speakers at the end of last year, and each of those speakers, like today, Dr. Lew Lim, help us to think holistically about the various ways of managing our symptoms. I would also remind everyone to just basically check your inbox for invites over time. There will be another session in a couple of weeks about breathing, swallowing, and voice in general. Just check your promotion inbox. Some of our emails end up in the promotion inbox, not in the inbox itself. To avoid that happening in the future, you just have to say to right click and save us as a contact. So No Silver Bullet for PD is the email address you will get it from, and save us as a contact to make sure that future messages don't get lost. We have a few very interesting speakers until the end of the year. But let's come back to today's topic, which is basically photobiomodulation as a promising treatment for Parkinson's. Dr. Lim received educational accreditations in engineering, natural medicine, and neuroscience from University of California Berkeley, Quantum University or Duke University, and is widely recognized as a knowledge leader in the field of light for brain stimulation. This is not the time for us to listen to Dr. Lim, who has, I think, very interesting facts to convey to us today. Dr. Lim, the stage is yours. You need to unmute yourself. You just need to unmute yourself, I'm sorry.
Can you hear me now?
Yes, we can hear you now. Perfect.
Okay. All right. Okay, thank you for the invitation. So I've been introduced. Thank you, Michelle, for putting all this disclosure and disclaimer, restrictions, what how you would take what I'm going to say. So I would say that we have devices that are being experimented for Parkinson's disease, particularly in Australia. We have our devices used in various applications too. So at the moment, we don't actually make claim of what our devices can do. Under the US categorization, the general wellness devices, but a lot of people experiment with it, and all we can say is, go according to guideline restrictions and say that particularly for the brain, in this case, is to help with mental acuity and mental functions and performance. So my talk is going to be somewhat scientific oriented because it's just our culture. And I hope it doesn't, put some of you to sleep, but I hope those who's got a strong background in biology, neuroscience or neurology, or having experience, done a lot of research, you might appreciate the depth that I might go into, but I'll try to avoid going too deeply into the neuroscience. So I'm going to share the screen. No. Oh no, wrong one.
There we go.
Try again. Let me share this. Oh, I can't get out. Okay. Right, here we are. Right. Photobiomodulation comes in many ways, in very many applications. So these are some of the various ways. You got to understand that we're not the only people by any means in this field. There is application like on the knee for pain treatments, or to treat arthritis, and there's hair growth, aesthetic, cosmetics. Particularly for sports, you have this casket-like device that people lie in and get whole body treatment. And there are panels and so on. So that's how photobiomodulation is being applied in life. This is a device that is pretty popular. It's called a Neuro that we do, but it shows you that it is a wearable device. There is a nose and a head application for it. So just to give you an idea, if you're not familiar with photobiomodulation, they are device-based, and this is what one example is like. Now, if we direct light from the way we do it on a head, the intention is to get a penetration from the head, from the nose, and to be able to modulate the brain. Now, some of you are probably very familiar with this content here. And treatment for Parkinson's are typically medication-based. If you're under treatment, or you have an interest, you're probably familiar with some of these. But they're mainly for the management of the disease. So it's not by any means a reversal or cure. And the popular ones commonly applied levodopa, which is a a molecule that some of it goes to the brain, is a precursor for the synthesis of dopamine for the brain. Then there are other substances that can enzymes that can inhibit the amount of these precursors that go to the brain. So you have COMT inhibitors, you have dopamine agonists that help with the receptors to receive dopamine, and MAOB inhibitors is to reduce the degradation of the levodopa and so on. Now, I think what's been effective, once your drugs are not shown to be effective, we look at the option of deep brain stimulation. There's other kind of stimulation where you inject, say, levodopa into your small intestines and have more effect. But deep brain stimulation has quite a long history. It started with this, and then when levodopa came about, it declined, and now there's interest into deep brain stimulation again, especially when the drugs are not particularly working. I want to talk more about the similarities in how deep brain stimulation is being administered, and where photobiomodulation is demonstrating efficacy. Now, it all comes down to recognizing that mitochondria plays a key part. There's been a history of research on mitochondria in degenerative diseases like Parkinson's, and we're big into Alzheimer's disease, so this is very key. And this is a recent discussion on mitochondria. It typically comes with this electron transport chain. So I won't go too much into detail, except that it showed here how they're measuring the dysfunction of mitochondria in cases of Parkinson's disease. But they are associated with some of the you can call pathogenesis or the causes of Parkinson's. And when there is a breakdown in, say, the parasites in the blood-brain barrier, it goes, this pathology goes to the brain and is often associated with the alpha-synuclein protein, which many of you are probably familiar with if you're looking to Parkinson's disease. So when there's too much, say, calcium ions are prominent in brain signaling. If too much of it, it damages the mitochondria because of the excitotoxicity. And then there is the mitochondria being damaged is not able to do this trafficking or repairing of the neurons and axons and so on. The bottom right is looks like a complicated illustration of how the mechanism of pathology actually works. But you have things like zinc and iron traces that may cause damages to the mitochondria in the brain, creating this oxidant-reactive oxygen species. And then you have this UPS, ubiquitin protease system that's supposed to clear, right, damaged cells, mitochondria, and so on that's been compromised. And the other system that's associated with autophagy. So when you're damaged, you're supposed to remove it. When the mitochondria is not functioning properly, it goes in this cycle that's not clearing the aggregates and not functioning properly at the same time. So the mitochondria is key, and that's where photobiomodulation, the foundation of photobiomodulation, comes in. Now you may wonder, how is it that light is able to work on the body, the brain, and produce these possible outcomes in research? And maybe if you use this before, you might experience the efficacy of it. And it all comes down in photobiomodulation. It's come down in its role as the foundational in photobiomodulation. So this is a nice, it's colorful and all that, but it's not as simple to understand. But very simply, on the left side, you see the same electron transport chain and the role of the cytochrome C oxidase, an enzyme in the last terminal, which receives the light, processes it, does a few things. Come and touch on these few things as I go on this presentation that helps with the improved functions in the brain or the body. Now, so just simply, photobiomodulation is on the foundation of the role of the mitochondria, which is in every cell. The mitochondria's main role, actually, as most people understand, is the production of ATP, which is the cellular energy. But it does more than that. It does all this signaling that helps with the functions of the brain. Now, this is an illustration of the various things that it does when you translate it and move up to a higher level to the tissues and why it is producing these outcomes. A lot of discussions have been centered on increased blood circulation. Yes, it does that. Improvement of the blood vessels and so on. But when you relate to Parkinson's, you want to be looking at things like what I mentioned before is, say, the decrease in excitotoxicity, the increase in neurotrophins that improve the networks of the neurons in your brain and the growth factors, to allow repair and stuff like that that's going on. And then in the meantime, okay, the circulation goes on, but it's, that spreads to all over the brains. So in this sense, photobiomodulation, because of the numerous pieces of mechanisms that are going on, it is actually holistic. in the way it treats the brain. And it does it naturally because it just uses light, So when we talk about mitochondria dysfunctioning, this is I say a very recent paper. Is quite brilliant in the way it summarized everything. When we looked at trying to stimulate specific parts of our brain, just like the way that deep brain stimulation is doing, it is actually possible with photobiomodulation, with delivering light to a specific part of your brain. Okay, this is invasive. It is a way of saying that, okay, you want to do like deep brain stimulation, which targets mainly the globus pallidus or the subthalamic nucleus. You can try and do that, but in photobiomodulation, you look forward to stimulating something that's more neuroprotective, which is where the dopamine is coming up from, which is the the substantia nigra pars compacta, which in the midbrain area. So that's possible. Now, why is mitochondria so important? Is functioning for, say, Parkinson's disease. And part of the reason is, of course, here you look at B in the right chart. Again, electron transport chain. But this part in C, it relates to, say, in those neurons that are particular to Parkinson's disease. Typically, the axons are pretty vulnerable, pretty thin, but it has a lot of dendrites going up, so it does spread out a lot. And then there is the release of dopamine comes in almost like a pacemaker. Now, all this demand a lot of energy. It demands more energy out of the mitochondria than possibly most other neurons in your brain. So that's why you need to have the mitochondria, because of its role in producing energy to be functioning very well. And I look at E, and because the electron transport chain. Okay, here they discuss about certain chromophores that receive the red light or the near-infrared light, which photobiomodulation is mainly about. It also frees the electron transport chain by releasing this element, this molecule called nitric oxide, so that it functions better. It gives you more reason why you want to target your brain with photobiomodulation, these multiple mechanisms that it can produce. Now, it differs from the way that deep brain stimulation is doing, because deep brain stimulation tries to enhance the function of, say, the subthalamic nucleus by delivering electricity. When you go into a deep brain stimulation surgery, typically the surgeon will test you while you're still awake and see how you respond in your tremors, or when you're asked to move, whether you can move or not. That is a little bit different than stimulating the response. But when you direct to the source of the dopamine, then you are protecting the brain, so you can try and release it on a pacemaking manner. So this is the theory. Now, I know that experiments are going on now. It started in early days. It was done in University of Sydney in Australia. They experimented in animals and mice. Now the professor, who is John Mitrofanis, actually quite a good friend of mine, has moved to France, where he is part of a group now looking at possibly experimenting with humans. But we have the options of the alternative, say if you don't want to be the guinea pig, look at non-invasive options, something like this. Now, this was so I talked about, maybe I talk about the history of what, the research in Australia. So So this is a case of Chris Lacey in Tasmania in Australia. He was the one who kind of advocated, hey, you know, I've experienced this, and you should really look into, people should look into photobiomodulation and how it may be possible. Now he used an early device of ours called a Neuro, and here is what was really kind of shaking up the Australians in around 2016. Before.
You coming? Yeah. Yeah.
So about 1.5 months, 2 months later. So Chris is kind of showing off, but I say that not everybody responds the same way. I think we were lucky that he was able to respond so dramatically, and word got around, and then this got into the news in Australia. A retired member of parliament, Max Burr, he said, okay, let me just put, you know, the theory is putting lights into your brain. So he put lights into a bucket and put over his head, and he actually improved. And that prompted a study in Australia driven by folks, John Mitrofanis had mentioned, and some people got together, got this made, you know, put together. People just do it the way they want, so you can find the red lights done in various manner. And looked at 6 subjects, and if you look at the chart on the bottom left, most of them actually improved when you measure, you know, the various signs and symptoms of Parkinson's disease. So that's quite dramatic. So it seems to be working, and very, very interesting. So we should all go deeper into this, right? And what was happening also in other parts of the world. This is a group of Brazilian researchers, Spanish researchers. They did a randomized controlled trial. And we always, in research, we always want to look at randomized control studies, because then you have proper control, and, you know, it's not placebo, and see whether it's really having an effect. So they did that, and they put a couple of LEDs, you know, red onto the front of the skull. Came up with a hypothesis that maybe it will affect, you know, deep enough with the brainstem and so on. But I don't know about that. But the bottom line is they have shown actually improve in the gait speed on the 10-meter walking test. So that is really, really interesting, and we should, you know, put the money on clinical trials like this. Now, in Parkinson's, how we would look at how studies should be done, and how we can try to be more precise in the way we use light to have a Parkinson's disease. And this is something that when you go deeper into studying the progression of Parkinson's disease, this is pretty well known, the Bragg staging. They usually come in 3 big groups. You know, 1 and 2 is the early stage. It affects the autonomic and smell. And interestingly, smell is always an early sign of where we are going with neurodegenerative diseases, like even Alzheimer's disease. Now, at this stage, you can see the early dysfunctional lesions in, say, the olfactory. Then it progresses through stages 3 and 4, when it moves. Well, even Bragg's group talked about vagus nerve coming out from, you know, from the gut, from the gut, and affecting more the thalamic area, which affect the motor symptoms. Then you advance into affecting cognition and emotion. Now, I like what this particular group is doing, and they're starting only just now. In fact, we're looking at very recent research into separating body and the brain. And I think this is going to go into refining how you would look at treating Parkinson's disease. Now, there's more and more discussion about the body. You know, the microbiome in the gut, it goes up to the vagus system and goes to your brainstem, and then it affects these substantia nigra in producing the dopamine that you want, and then affects the other part of the cortical area and even the limbic system. Then you have the brain first, which has been what a lot of people have been thinking of for quite a long time. Now, no one really knows exactly how it starts. For the body first, you might say, yeah, it could be the microbiome. If you affect the microbiome in a bad way, you propagate more of the bad bacteria over the good bacteria. You start getting this, and the microbiome, the gut, has been seen as the second brain, producing dopamine and other neurotransmitters. Now, you could start from the brain actually, and it doesn't actually start from the substantia nigra, the source of the dopamine. They're looking at the research imaging where they're trying to see where, basically follow the money. The money is the marker alpha-synuclein, how it is progressing, and that's how they separated the body first or brain first. Now, brain could start with the olfactory. So it could be something affecting your sense of smell very early. Could be a virus, could be infection, it could be neurotoxins. It could be, it also affects the amygdala and the limbic system, which is where the emotional processing is being done. Then it's spread into, the midbrain, substantia nigra, producing dopamine, and then it goes down to the locus coeruleus, which is actually quite important in the sleep cycle, your cognition, many functions. And then it goes down and is also exhibited in the intestines. So the way this group is measured is measuring, how advanced and even the heart is being affected. So that comes to us appreciating the importance of the microbiome, the gut-brain connection. Now, this is actually not published yet. This comes out of Australia. There are a couple of studies going on in Australia. This is quite the major one because the group in Sydney, headed by Anne Liebert, looks at the gut as well as the brain. Now, what they're trying to do is to treat both. They used a device to treat the brain, the gamma, which is pulsing at 40 hertz, affecting. That is theoretically helping to clear this Lewy bodies, the aggregation of the alpha-synuclein molecules, and helping with the cognition and so on. And also, they were directing the near-infrared light to parts of the cervical area and also to the gut to theoretically improve the microbiome composition. Now, they've done other studies and have published earlier showing that if you can direct red light, a near-infrared light, to a microbiome colony, you can actually increase diversity. So diversity is always a good thing in microbiome. Now, they looked at various scenarios. This is you look at the clinical. Now, what you want to do here is look at this is a heat map. So where the darker areas, it shows that there's more improvements in outcome measures. they looked at various typical indication of Parkinson's disease, like TUG is timed up and go. So if you're like facing rigidity, is how well you can get going, and mobility like walk speed, stride length, TUG motor, and cognition, the balance. This is like a dementia measurement of your cognition, and other this fine motor skill is a 9-hole test. What is it, precision test or something? To see how well you're doing with putting the holes in various areas. So your motor skill. And then the tandem standing and single leg standing and see how well things are going. But you can see, they're quite good maps. And then you're looking at home after a certain amount of time, everybody takes home a device, treat at home. And then you get these heat maps too. And you can see a number of dark areas when they compared against wait list, which is people was waiting to get treated. There was some response, which may be placebo, but not as much. So this is very interesting that this is a pretty detailed study on the Parkinsonian symptoms to photobiomodulation. Now, there are more than just the gut brain. When you look at the brain, is more than the areas that I've mentioned before. Typically substantia nigra, or you're looking at control, which is the basal ganglia area, the subthalamic nucleus, the globus pallidus, where they do brain stimulation. But other areas of brain are also involved in Parkinson's, which is not studied quite a lot, that we should pay attention to. And an area which is pretty deep, it takes, you got to remove one layer of the brain before you can, the outer layer, before you can reach it, as you can see on the right, so it's deeper down. But we should also try and reach it, Actually, if you want to treat, broadly speaking, the stimulated areas with deep brain, you are looking at, say, subthalamic nucleus, substantia nigra is just a little bit below it. They are just behind, actually, insula. If you can direct light to this area, you are, treating multiple areas that are affecting Parkinson's. Now, Australia, your University of Sydney, actually they did this in 2019, wanted to look at movement and see if they put on a device that we have, which is the neuron on the head that you saw in the illustration, but this is passing at 10 hertz, and do this, evoked activities like moving of fingers, right? This event-related potential, ERP, you can call it. They found that when they have this lights directed to the brain, there is more inhibition in the areas that affect movement in that area in the basal ganglia, which affect, like particularly here in the putamen. Now, what is it teaching us? It shows that inhibition is necessary to control movement. That's why Parkinsonian symptoms of tremors that are not able to be controlled, but delivering light can help to control it. And not forgetting, that part of the brain has probably the highest number of neurons versus, these are the back of the head. The cerebellum, it is a part of the brain that somewhat mysterious until fairly recently. They want to know more about it. It doesn't seem that important, but they have so many neurons. Now, in Parkinson's, when you control, on the right side, you see the healthy controls in Parkinson's patients. And they do these tasks like finger tapping, counting, conscious tasks to see what what is happening in the brain, how the brain is trying to process it. Now, the red that you see are the areas of the brain response. Now, where there are more red, it means that the brain is really working to try to make it happen. So having red is an indication of which part of the brain is struggling. And you can see on the bottom right, when you look at Parkinson's patients versus the control, there is a lot more red in the cerebellum. So in the cerebellum, there is processing going on too, trying to see, trying to, to help the brain or the body or whatever to function better when you are handicapped. So the cerebellum is quite important. Now, there is some research going on to look at the sensory motor area, which is where you are sensing, you have sensors and you respond with your motor and try to move various parts of your brain. So the sensory motor area is kind of like here. And they found that if you can train the sensory motor area to function better in the sense that it's normalized, you get a better response. So this is a potential target on how you want to help a Parkinson's patients to improve, is try to influence the sensory motor area in the brain. Now, when if say we were going to go to do a more and improved study on trying to, to improve Parkinson's disease, at the moment we would try and do it this way. We would, I didn't say here, we would deliver, light can pulse at various frequencies. We can do it the way we want. If we want to heal traumatic brain injury or just general stuff, we pulse at 10 hertz, just because animal studies done at Harvard show that 10 hertz alpha helps to heal the brain from trauma. But Parkinson's, like Alzheimer's disease, we have a study that's going on with Alzheimer's disease now targeting 40 hertz, which pulse faster. And why do we do 40 hertz is just because part of the reason we do it for Alzheimer's disease, because it helps in memory encoding, as done in various studies, but it also helps the certain brain cells, the microglia, to help clear these unwanted deposits. And Parkinson's it will be the Lewy bodies accumulating. It's probably accumulating in regions called the default mode network. So with pulse of 40 hertz, on that area, you could help to clear these Lewy bodies that are kind of handicapping the functioning of the brain in Parkinson's disease. But the targets we go for would be, how we have designed it is to target olfactory. As I've pointed out, olfactory could be an early source of the brain Parkinson's disease, or brain first Parkinson's disease. It's close enough to the amygdala. There's a direct channel between the olfactory to the amygdala, other than the memory area. And then it could also, the way we position it, could be moved further forward to target the insula, right? So for Parkinson's, I would say, although we're getting good results, say in Australia, with the way this is positioned, we want to move this particular LED to hit the insula, and that could cover the midbrain, and then the brainstem could be covered by the intranasal. We are just hypothetically speaking, thinking that the intranasal could be hitting the brainstem. Of course, the the last discussion piece was on the cerebellum. We try to put it, which is at the back of the head, as a separate device. So that is what we do as a possible universal treatment. But later on, we want to get more precise, and we've been talking about the the gut, the body first, or the gut first, part of the the expression of Parkinson's disease. And we could be targeting directly on the gut, the stomach area, or position it on the vagus nerve, which is the most, I would say, not exposed, but the part of the nerve that's closest to the surface. So that's linked to that, linked to the brainstem, the autonomic area. I didn't have any time to talk about that, but this is all related in Parkinson's. Then we can do this for the existing device for the sensory motor area, or we could have something more precise like this we're developing right now to target both exactly where it is, this sensory motor area, the insula, and we can add one to the cerebellum. So this is where we're headed for. I want to leave some room for discussion if you bring up anything. But I say generally, although we are our devices are, say, for general wellness, generally improving your brain function, in your mental acuity, but we've always been conscious about using the devices for research. And when somebody comes up and say, "Look, I want to do a research on Parkinson's disease," and we could say, "Okay, you could do this. You could modify the positioning of the device, or we could, do something that's a little bit different and target for research." And what we want to do is get really precise and significant outcomes so that we can one day do a bigger study and say, do this, and we think, okay, if you want generally, we can have this particular model and say it works for Parkinson's, or if you are showing certain symptoms, maybe this is the way to go. So what I'm saying here is mainly our thoughts for how we would approach treatment for Parkinson's in the future to be able to help the researchers to begin with. So thank you, everybody. These are, I always want to thank our staff. One of them is Nazarin, who is part of the people here. We do a lot of research. We're heavily research oriented, and we work very closely with a number of top-level universities to help us to help with the future of photobiomodulation, particularly for the brain. Right, so thank you all.